Okay, in this second part of looking at significant figures and scientific notation, we're going to look a bit more at some of the maths involved, such as rounding numbers, multiplying and dividing, or adding and subtracting. Okay, so we saw this number in the last video. Let's write it out again in scientific notation. So it's 3.04016 times 10 to the 7. Now we remember these two zeros are placeholder zeros, and these first 6 digits are our significant figures. So that's our sig figs, and they're just placeholders, just telling us where the number goes. And you can see that's why they're not included in the scientific notation, those last two zeros. We're just assuming that they weren't actually measured. Now, a common thing to ask is round to 3 sig figs. So round to 3 sig figs. Well, let's do it first of all on the scientific notation. That's the easy one to do, to be honest. So we look here and we can see, we look over the fence. We've cut it off. 3, 0, and the 4 are 3 significant figures. And so we've just got to make sure that we're in the right ballpark here. And we can then just cut off all that. And we just say now the number is 3.04 times 10 to the 7. So remember, you're rounding off. 0 to 4, stay on the floor. 5 to 9, climb the vine. And we're going to do the same thing over here. And we look over the fence and we say, nope, 0 doesn't make the 4 go up. But what's happened is we've actually changed. So the placeholders now are all of these numbers. So placeholders are always zeros. That's a 0, it's a 0, it's a 0. They were already placed at all zeros, but already 0. So in the full notation, like we normally used to, 3, 0, 4, those are our 3 significant figures. And then the rest becomes zeros, 0, 0, 0, 0, 0. Okay, that's how you round off to 3 significant figures. Let's try it again. Let's try 2 sig figs. So rounding to 2 sig figs. So let's try that again. So we've got 3.04016 times 10 to the 7. We count how many sig figs we got. So we got 1, 2, we cut off there. So we got 2 to the left. And then we look at the 4. Does it affect the 0? No, it doesn't. We can cross off that. 0 to 4, stay on the floor. 5 to 9, climb the vine. All right, and then we can see quite clearly we've got our 2 sig figs. They're right there. There's our 2 sig figs in our coefficient. Remember that one, that's called the coefficient. And then we still got the magnitude on the right. Let's do it on this number though. So if we do it on the normal way you write numbers and we look over the fence, and it shouldn't surprise you, it's the same thing. But remember, all of those become zeros again. So 0, 0, 0, 0, 0, 0. They're now all placeholders. They're all placeholders. They're not significant anymore because we've gone to 2 significant figures. Where are my significant figures? These are my sig figs over here, sig figs. So if we rewrite that number, you can see it's now 3, 0, 0, 0, 0, 0, 0, 0. And you can see why the scientific notation beats it, because it's quite clear. 2 sig figs. But this one, how many sig figs? We don't know. I mean, the question told us to go to 2 sig figs, but how do you know this 0 is special or not? So is that a sig fig or a placeholder? We don't know. Well, there you go. Okay, so let's try a small number now. So in scientific notation, 18093 times 10 to the negative 3. Where'd that negative 3 come from? Well, remember we're going smaller, so we're going 1, 2, 3. That's the 3 moves, and using the decimal point cheat way of doing it, that means 3 moves of the decimal point to the right is negative 3. And let's do our usual thing, which is 3 sig figs. So let's round to 3 sig figs. And let's do it on the the easy one on the scientific notation. So we're going to go 1, 2, 3. That's right there. We've got 3 significant figures to the left. Then we look at the 9. Just the 9. Don't care about the 3. Just the one directly over the fence. And we can see 0 to 4 stay on the floor. 5 to 9 climb the vine. That means we're climbing the vine. So that's 1.81. We don't care about the rest of that stuff. And we say times 10 to the -3. And if we then look at doing it on the normal kind of number, the one you're used to, you can see it gets a bit tricky because the significant figures start here. Okay, so when you're counting the 3, you've got to ignore, these are placeholder zeros, so ignore them. They're all placeholders. I'm going to go 1, 2, 3. So we end up at the same spot that we did last time. Look over the fence. And we've got to rewrite that number as 0.00181. And we don't have to write the rest of the zeros. Oh, those became zeros, but there's no point writing them, is there? You could write an infinitely long line of zeros. It wouldn't make any difference. And there we go. That's rounded to 3 sig figs. You can start to see that scientific notation definitely is easier and clearer on these things. Okay, before we go on to any maths, I'd like to introduce you some golden rules. They're actually very similar related concepts. But our first one is mass does not improve measurements. So if you measure something to the nearest centimeter, you can't use millimeters. You can't say, hey, I did some maths and it's to the nearest millimeter. No, you can't. So you cannot increase the number of significant figures with a calculator. Okay, that's pretty much the same thing as the first one. You're only as accurate as your least accurate measurement. So if you do a whole bunch of measurements to the nearest millimeter, and then you do 1 to the nearest meter, well, guess what? That's the accuracy of your answer. So your answer needs to be rounded to the nearest meter. The lowest number of significant figures in your calculation is the maximum number of significant figures in your answer. So whatever you choose to start with, you've got to make sure your significant figures are consistent throughout. And we'll go through a couple of examples here to show some common traps. Now this is where it gets a little bit weird. If I said to you 5 times 7, what is the answer? And I'm sure a lot of you would say equals 35. And I'm now going to tell you that no, it doesn't. And you're like, what? Well, let's remember what we talked about with the golden rules. We said that maths does not improve your accuracy of your measurements. So this is one significant figure. And this is also one sig fig. But our answer over here, 35, has 2 sig figs. That's not allowed. The most accurate number we had, which was either the 5 or the 7, only have one significant figure. So our answer must be rounded to 1 significant figure. So if we look at the number 35, we have to say, well, cut it off. There's 1 significant figure. We look over the fence. That means that becomes a 4. And that becomes a placeholder 0. So the correct answer for 5 times 7 is 40. Now that's going to sound a bit weird, but that's just because we're looking at the answer now only has the 1 sig fig. All right. Okay, let's try some things the traditional way you're used to, and then we'll see what happens when we do that in scientific notation. So I've got 2 numbers here, 4,900 times 270, and if you were to hit your calculator, you get 1323000. Now let's do our sig figs count again. 2 and 2 and 4. So that answer needs some trimming off. So here we're going to cut it off at 2. We look over the fence, and then we change that to a 0 and that to a 0. They're now placeholders. So our actual answer should be 1300000, which last time I checked was 1.3 million. So with our accuracy of our measurements, we measured 2 significant figures on both of those multiplying numbers, and we've got 2 significant figures in our answer. In scientific notation, 4,900 would be 4.9. We forget about the zeros because they're not significant, they're just placeholders. And we times 10 cubed because that makes the 4 into the thousands column because we're timesing by 1,000. And then that's times 2.7 times 10 squared because 10 squared is 100, and that means that that 2 would now be 2 lots of 100, which is what we got, 270. Okay, now this is where it gets a bit interesting because though we're kind of looking at this number times this number, it doesn't matter which order you multiply things, does it? So we could actually grab this guy and multiply them together on their own. So we know that if you've got 10 cubed times 10 squared, if you know your index laws, you know that you just add the powers. So that'd be times 10 to the 5. So whatever we got, we can do times 10 to the 5. Now we've already kind of got the answer above about the thing, but if you think about it, this is roughly 3 times 5. 2.7 is 3, 4.9 is 5. So 3 times 5 is about 15. So you can see that we're actually getting a number here, which is going to be 13.23. And you might be happy with the answer. But let's look back at our normal calculation at the top. If we would put that into scientific notation, that would be 1.3. And to get there, to go 1, 2, 3, 4, 5, 6 times 10 to the 6. So here's a little trick that you may not have noticed, that we can't have this 13 over here, can we? We've got to take another move. And so it's going to be 1.323 times 10 to the 6. And then we still got to do our thing where we cut off. So we've got to cut off. That doesn't change anything. We can get rid of those guys. And so we get the same answer. But you notice, like when you're doing the maths, you sometimes do have to look in this area that number might have gone past the 1-digit limit that we have. We say that in that area, we can't have 13. We can only have 1 to 9 in that area. So we have to do another move at the end just to correct to scientific notation. Let's just do another example. 6.059 times 43,000. And if you hit your calculators on that, you'll get 260,537. Okay, let's try that in scientific notation and see what happens. All right, so 6.059. Well, that's already kind of scientific notation, but you got to times it by 10 to the 0, okay, which means multiplying by 1. So there's an index law if you've forgotten. Anything to the power 0 is 1. All right, and then we're going to times that by 4.3. That's 1, 2, 3, 4 moves if you look up there. So I times 10 to the 4. And that equals. Now we can do that quickly, just check our magnitude check. So if we do a magnitude check, we've got this times this. We add the powers, so 0 plus 4, that's 4. So it's going to be times 10 to the 4. And we should end up with, well, we've got 6.059 times 4.3. If we actually did that, then you would find we should have 26.0537. Now, our problem here is if we look here, 4 sig figs, 2 sig figs, 1, 2, 3, 4, 5, 6 sig figs. So that's not allowed. And we've also got a problem that we've got this 26. So first of all, let's put that into proper format. So that's 2.60537 times 10 to the 5. We've had to do another move, and we could see that at the top there, that is the same number, 1, 2, 3, 4, 5, 2.60537 times 10 to the 5, but we've got to cut it off. Now this is our lowest number of significant figures, so we cannot be more accurate than our least accurate measurement, and our least accurate measurement was 4.3 times 10 to the 4. Even though it was a bigger number, it was much less accurate, so we've got to cut it off there. We look over the fence, and then the rest of these can just disappear. And so the final correct answer is 2.6 times 10 to the 5, which at the top here would be 2, 6, 1, 2, 3, 4 numbers.